Well, hello there, and welcome back for more Advent of Code, day 19. So where were we? I think we did the parsing of these things, the workflows and parts, and we could successfully parse these things and print them. And now we need to implement the processing. And again, I forgot to put a stopwatch. Let's do that real quick. Stopwatch and run. Okay. So we did the parsing, and that took some time. But of course, everybody knows that parsing is the real complicated thing, right? And then doing the calculations is the easy part. That's usually not the case for Advent of Code, but in this case in particular, the parsing was a bit involved, and the computations actually, if I remember correctly, they weren't that difficult. So basically we have to process each of these parts through the workflows that we have. This explains, like, in a given workflow, when you are evaluating, considering a specific part, so you basically evaluate each rule in order, and otherwise you go to the final rule, which is like a fallback thing, which always matches, and that's basically the result of processing a single workflow, and then workflows can jump from one to the other. So that's basically what we need to do. So let's sketch it out. We did the parsing in a very top-down manner, like starting from the top and saying I parse inputs, and I just did full screen there. Parse input, and then going down from top level to lower levels. Like parsing input is then split into parsing workflows and parsing parts. This can probably be in lines like this, right? Yeah, that makes this a single line. And then parse workflow that delegates something to the workflow parse, and then this delegates again to rule parse, and so on and so forth, which is a pretty traditional way of doing sort of object orientation, you could say. Like you have different objects, and they delegate the specific jobs to other objects, basically. So, sorry, I had to take care of my cat. She was about to jump to the desktop and cause trouble because I have some tea here with a cup of tea because it's night, of course. No time for drinking coffee. All right, so I was thinking of maybe we can do implement the calculations in a similar manner, like going top down. So what should be at the top? We had to process each of these parts through the workflows and tell if each part is accepted or rejected. And if it is accepted, we are computing this, sum all the numbers in the parts and then adding all of those together. So let's write that top level code. Say this is what you get if you add together all the rating numbers for all of the parts that ultimately get accepted. So on a given part, I guess, or this in a condition, call this thing category index. I guess should be called rating index or something like that. I'm hearing some weird noise. Probably some. This has been. There have been a lot of protests today, so maybe it's coming from the outside. Okay. Ratings sum. Let's call this thing. We were using 64 bits for everything, so let's use that. So we're going to basically iterate over all the parts and process them with the workflows. So we're going to say parts iter map. We basically want to filter the parts that we accept. So let's do a filter, I guess, first. And we're going to have a part, and let's say process part. This is going to take, well, a part and the workflows, right? Workflows. And this is going to do all, like, the whole processing for a single part, and I guess give back a Boolean, whether the part is accepted or not. And then, well, we have filtered them. I guess we need to map the part to, like, adding all of their ratings. And the parts themselves are just arrays of 4 numbers. So do arrays have like a sum? No, but we can do iter sum for sure. And then after that, we sum all of this together. Okay? Process parts, we can generate this, and it's going to take a parts and workflows, and yeah, that's it. So parts. Now, aren't you a reference? You're a double reference, actually. So I guess we can use, I mean, parts is just 4 numbers, so taking a reference or like the thing by value is not really that different, but okay. And this sum surely needs some type annotation, sure. Okay. And you can know this because value. Sure, so that is because I'm not sure why this is though. If I take the part by value here, you are still, but I guess I can into iter you. Why not? Oh, it's U62. Oh, okay. This is 64-bit numbers. That's why are we using this for parts? Because for everything else, oh, I guess we were using U64 bits for everything, and I got confused. Maybe I got confused from the previous puzzle. So yeah, sure, use U64, and I don't think I need to do this now. No. And this into iter is not doing anything special, so thanks Clippy for that. And ratings sum is not being used. Let's use it. Ratings sum. Okay, so this is sort of the high-level code. And now the delegation should continue. So how do we process a part? Yeah, all the parts begin in the workflow named in. So there must exist a workflow named in, and we start there. We can delegate to the workflow and say, hey, process this part. And when you, like, we have modeled, basically the workflows have rules and a fallback thing. And we have also modeled this output thing, which is like, hey, it's either rejected, accepted, or jump like to another workflow. Yeah, this is workflow, I don't know, jump or whatever. And this is just the ID of the next workflow. So I guess when processing a single workflow like that, the result is going to be one of those. until you either hit accept or reject. Right, so this is basically, this should be pretty easy. Let's say we're gonna have like our current workflow ID, say workflow ID, which initially is gonna be in, and we're gonna loop. I think writing a loop like this should be fine for this. We need to get this workflow from the workflows hash map. So we're gonna do workflows get workflow ID, sure, and this could fail, of course. We could also have used square brackets here, like we could access the workflows like this, but this panics if the thing doesn't exist. So I was wondering, the only way that this could fail is that there are some bad IDs on the input, like a malicious input or like a broken input could make this fail, sure. And I don't want that to happen, but also it's a bit ugly, I think, that these process parts could fail for a reason like that, like after parsing. I feel like this is a hint that maybe we should take care about workflow IDs while parsing, and then, I don't know, use like indices or something like that, that we know are valid. And that, by the way, would get rid of all of these lifetime annotations, because IDs will no longer be string slices. They could be like a single number. So that's sort of a hint, I guess. We could just unwrap here and leave that for later, or make this return a result of bool, which I guess we would have to carry on forwards, which is not very nice. So yeah, let's unwrap this for now and leave a to-do handle these results, handle this error. We could also say, like, we could make it like a logical problem, this, and say, okay, this is false, you know, and just return false if the get failed, which is also like robust in the way that, in the sense that we wouldn't be failing for, like we wouldn't be crashing for an invalid input, and it would just say, okay, this is rejected, you know, the input was invalid, like what do you expect? But I don't know, that doesn't seem very graceful. I would prefer to catch that during sorry, I'm being a bit slow, like during parsing, of course. So yeah, handle this error better. We can say expect here, I guess, and say whatever, workflow ID not found, or invalid workflow ID. Okay, so this would give us a workflow, I guess, and then we can ask the workflow to process a part and just pass the thing right on. This will give us back a result, so let's say, or an output, and we can now match on this output and ask the, so yeah, we need to generate this process method, Sure, this is gonna give us back an output, and I don't think that this will be optional, or I hope not. This is a part. Again, I don't know why it's being generated like that, because I was passing a reference to a part there, so somehow it got lost. Hello, my cat got to my lap. So okay, let's leave that to do. Come on, Simona, you can sit more comfortably, please. We can generate this match arms once the cat decides how she's going to to sit. Okay. All right, so if the process in the part in this workflow says that the part got accepted, we can just earlier return from here and say true. If it's rejected, we can say it's false. And if it is another workflow, like jump to another workflow, we can mutate this workflow ID and change it to this ID. And then we loop again and handle that workflow. So yeah, that was simple enough, like pretty high level stuff. Now we have to like delegate and get into here. How do we process a part inside of a given workflow? So the workflow has rules and a fallback. So we will sort of delegate again to the rule, I guess, and say, hey, self rules, what do I want to do? I basically want to try the rules in order, and I don't need to try all the rules. Like the first one that matches, that's it. So I guess we could do like a find rules iter, find the rule that matches and get the output from that, right? Yeah, or maybe even like find map, and we're gonna have a rule and say, hey rule, match this. Oh, you cannot not match, but maybe process again, like the rule can process. I want to call it match, but how do we call these things? You can say just process, right? Contains for rules. I'm missing my glasses. Reading glasses time. Okay. Yeah, this is basically what we have already encoded. If a part is accepted or rejected, the part immediately stops any further processing. Sure. So let's just call it process again, like this rule will process this part. And let's assume that this process will give us an output if the rule matches that part. Like the condition of the rule matches that part, but that could be like the find map itself will give us an option. So here we can say unwrap, or what is the default? Well, the self fallback output. And here we can generate this thing again. And look at that, it generated the right types. It's an option of an output. And this sadly needs a lifetime annotations, I guess, or not, maybe not. Yeah, if it doesn't need it, let's not put it there. The workflow here either, I think, yeah, let's have to light those things. So this process, again, should take a reference to a part. And how does a single rule process a part? Well, we need to see if the part like matches the condition, and if it does, we just return the output, and if it doesn't, we return none. Cat is still turning around in my lap. She is not deciding how to sit, being indecisive. So what did I just say? We can say if self condition, and again we can delegate here. If it matches this part, then we'll return, well, we can just say then it's gonna be sum and self output, otherwise none. Sure. And this programming like top down is kind of funny because it's like you do very little each time, and it's like, yeah, take care of this, and you just delegate forwards. Of course, this generates a lot of code, and probably would be much shorter to write everything like in a single function. But I mean, when you break things into objects like this, it tends to favor this kind of code, I guess. So, my cats. Do you hear that? That is my other cat, the one that is not on my lap. Wait a second. Okay. Door opened for the cat, of course. Where are we? Matches for a condition. Okay, we want to see if a rule matches a condition, or a part matches a condition. And the condition had like, yeah, what category? So conditions are basically, let's see a sample here. Things like this. Say, hey, if the part's S value is less than this, then jump to px. The then jump is the part of the rule, and the condition basically is this thing. So we need to like read the value on the part that corresponds to these different letters, and apply like the operation, Boolean operation, greater than or less than, with the value that the condition has, which it has a value here. So okay. That seems fine. I don't know where we were. I wanted to go to, oh, look at this, unwrap or. You don't want to take this because it would move this thing, sure. And this is an output which is not copyable. Well, we could return a reference here, I guess, or we could just copy, and I think this is trivially copyable, so let's make it copy. So yeah, clone and copy you can be. And then we were in condition, to say if a condition matches a part. So here I think we're gonna need the different values of the part. So this I call x mass, little Easter egg, I guess, there, or Christmas egg. And we should, well, oh no, we don't need to extract this. We don't need to extract this because we have the index. Like this thing on the condition, like this first like category index, this could have been an enum and just have a 4 value enum of x, m, a, or s. But I just put here a number from 0 to 3. So the index of that category or that rating on the part itself. So we can access it directly. So let's say let part value be the parts on self category index. And then, well, we want to do either a less than or greater than, but that is what self operator is. So I guess we can again delegate to the operator to be apply. I guess we can apply an operation or operator to part value and self value. So this is basically the left hand side and right hand side of the condition. And we should return this. And again, this should be the last delegation, hopefully. So yeah, we have an operator. So in here we can be more abstract and just call these things left hand side and right hand side, and do a match over self, and do your magic. And if the operator is greater than, we're just going to return a left hand side greater than right hand side. And if it is less than, of course, left hand side less than right hand side. And that's it. That should be all the logic. Let's see if I did this correctly for the sample. So it ran and it returned 19 something. Is this the expected? Yes, it is the expected output. Awesome. So let's now run the actual input. And it is 400 something thousands. Is this the correct output? Yes, it is the correct answer. Awesome. So that was pretty easy, actually. I would say it like jokingly that parsing was the most complicated, but for this particular puzzle, yes, the parsing was quite more complicated, I would say, than the actual processing for part one. Now let's see what part two is about. I have no idea where this goes, but here there is a bigger number. So even with your help, the sorting process still isn't fast enough. One of the helps comes with a new plan. Rather than sort parts individually through all of these workflows, maybe you can figure out in advance which combinations of ratings will be accepted or rejected. Combinations of rating. Each of the 4 rating xmas can have an integer value ranging from 1 to a maximum of 4,000. Of all possible distinct combinations of ratings, your job is to figure out which ones will be accepted. Ooh, brute forcing, this is a big number. In the above example, there are this number of distinct combinations of ratings that will be accepted. Consider only your list of workflows. The list of part ratings that the elves wanted you to sort is no longer relevant. Yeah, we just need the workflows. How many distinct combinations of ratings will be accepted by the elves' workflows? Oof. Now things got more interesting. Now I also have my 2 cats on my desktop, occupying some ungodly amount of space. So okay, this got quite interesting. Part 1 didn't require any clever computations. Part 2 is all about clever computations. So yeah, look at this number. So this is a million, this is a billion, this is trillions. So this is quadrillions of things if I didn't count, right? Billions, trillions, yeah, quadrillions. Awesome. So that's a big number. We cannot brute force this, and the Cartesian product, like of 1 to 4,000, is, well, 4,000 to the 4th power, which is gonna be a big number. Let's see how much. 4,000 to the 4th, it is, well, this amount. We can have it, so that's a million, again, that's billions, that's trillions. Well, wait, isn't this less than? Am I messing something stupid here? So isn't this number less than this? Oh no, this is the maximum, like the Cartesian product of all the possible values that the parts can have, and wow, this is somewhat less. So okay, by the way, this should be the answer to the sample. So how are we going to go about this? And I guess is this sort of an interval math kind of problem, like the, I don't know which was which problem it was that had like intersection. Day 5, wow, already day 5 was quite complicated. But I don't know if this is like a maths interval logic, because we don't need to, I don't know if we'll need to like intersect intervals and so how do we go about this? Let's see the sample. We start at in, and we know like in we are either going to go to px or to this, and this is split by the s value. So if s is less than this, we're gonna go to px, and otherwise we're going to go to this. The default of this is rejecting. So okay, we maybe could go like from rejections, like floating rejections up, although what we want to know is the accepted part. So we could look at the difference. Oh, this workflow, for example, is kind of interesting in that it asks a condition and then accepts, but otherwise it also accepts. So this workflow is always going to accept no matter what it receives. That is interesting. We could look at all of the rules that say, hey, accept, and for all the workflows, and from there derive, like we, for example, looking at this CRN workflow, we know that if we get to this workflow with an x value greater than this, will be accepted, right? So yeah, that's just a truth thing. And to this workflow, we are jumping from this one in turn jumps from this one. Px is the one that is at the beginning. Okay, so like we can kind of follow that line of reasoning, and I think we're going to need to do something like that, like collect the conditions that lead us to being accepted. So let's try to find like a simple path from the initial initial workflow into acceptance. So here there is one, I guess. If we fall into in and our s is less than this, we go to px, and in px we have three rules, considering also the defaults. But if m is greater than this, then we accept. But not only if m is greater than that, we also have to not match this rule in order for this to match. So we also, like, this is basically a condition saying n greater than this and a, like this not matching, so a greater than or equal to this. Okay. It gets complicated. So whatever matches in a workflow, yeah. So, okay. We could sort of follow this, I think. And are all of these workflows like connected back to in? I would guess so. We can kind of check it. Yeah. Yeah. GD we have already checked. This one I think we, yeah. QX goes to QQ, yeah. Yeah, I guess everything is going to be connected. Sure, and PV, this one which we have already checked, sure. So all the workflows like flow up to the in workflow. Or I guess we could say also like getting from the in workflow, you could reach any one of the others. Although maybe there are some conditions where you cannot, like simply cannot reach. Okay, so how are we going to go through this? It's kind of a recursive thing, like a recursive kind of definition. Imagine like we can get, I want to find like a giant condition, I think, probably combined by and, or maybe or also, which is ands and ors. And then from there, sort of, that's one thing. But then I would also need to, yeah, kind of like combine the intervals, like know which intervals of values are going to match that. And afterwards, once you have like the, you only need like the cardinality of x, m, a, and s values. If you know the cardinality of like those intervals that will be accepted, then which you just multiply those together, I think, because you can combine them in any way. Because all of the conditions are also like simple conditions. No conditions are like depend on two things, or saying s greater than m or something like that, which would be bonkers to me. This kind of sounds like one of those like optimization problems, or I don't know if optimization is the right word, but things that can probably be solved by like a rigorous mathematical thing, like or model like simplex or something like that. I know that those things exist, but I don't exactly know what they do or how to use them. So, oh, and look at this. This is also an interesting workflow. This workflow will always reject things. Interesting. But I think it's kind of the same, like going from here in the example, there seems to be more acceptance than, or accept conditions than reject conditions. Yes, there are, but I mean, that's kind of anecdotal, right? Like that won't make a huge difference. So here there are 520 accepts and 560 rejects. So they are basically the same. And I guess like every number should be accepted or rejected at some point. So whatever is not accepted is going to be rejected. So the two together should add up to that number, like to 4,000 to the fourth, right? Okay, let's try to write down what was the path that we found. What's this, right? Going to px. Okay, so we can sort of write this condition. Let's have, I don't know, a new thing here. Let's write this condition that we know. So if m has to be greater than 2090, and also this is an and because this condition has to be false, which is that then means that, well, we can say not a less than 2006, and let's keep sort of these things like this. Oh, I'm very used to doing Control S. So okay, these two things had to be, but also in order to reach px, we also need that s to be greater than, like, to this condition should be true. So I guess that's another, like, you combine this with the condition that leads you to that workflow. And I'm noticing something interesting here. I'll tell you what, but this is basically the condition that will. And from this, well, we could translate like negate this thing, like understand that this is the same as saying a greater or equal to this. Just realized that on the settings, I used to have font ligatures and I no longer have, and I want to have them for the, how was it that you could go to the settings file, ligatures, yeah, edit, yeah, this is what I want. Give me those things back, please. And look at that, greater than symbol, awesome. Okay. So what is the full condition then? S has to be greater than this, but it also has to be greater than this. So this is just the same as saying S is greater than this. And M has to be greater than this. And then the other two letters, S and X, can be anything. So that's one thing. That's one way of reaching, I guess. And can we go top down? Can we say that, I don't know, because I was thinking about this from the leaves up to the in, but maybe we can think about it from the other way around. Say, okay, we can accept this if this, like whatever the conditions of this rule matching, so if this is true and whatever extra conditions are needed for accepting, or if whatever the conditions are for this workflow. Okay, so we can have ors, I think. That's the thing. But we can convert ors to ands by applying the Morgan rule, right? Should be possible, I think. I don't know if that's a good thing, but it is possible. We didn't consider like these other cases either. Okay, what I was noticing before, which I think is kind of relevant, is that the workflows seem to only appear on a single rule. Like each workflow does not appear on multiple rules. And that is, I think, kind of interesting. Yeah, that makes this thing to be quite like linear or like linearizable. Like we know that there are no loops, for example, in here, which simplifies things quite a bit. This is true for the example. I don't know if it's true for the actual input. Like if we search for these things, if we search for this, yeah, there's only 2 of this. If we search for this, there's only 2. Great. So that's nice. That's pretty nice. And we have how many workflows? Oh, these are parts already. 530. So my intuition is saying that this is probably true for everything. So yeah, since there is like no loops or something like this, we can sort of make a giant condition, I guess. That's interesting. So yeah, okay, we can sort of think, like, I think I can figure out how to make like the giant condition, but then converting that condition into like actual ranges of values. Well, if it's all ands, I think it's just an intersection of values, but I don't know if it will be all ands, right? Yeah, I think that in order for this to, like, in order we did all these things with ands starting from this, because we went for like from a leave up to in, but this is just the thing that makes this accept succeed. But we can also match other accepts, and that would be this combined with some, like, the total condition would be, okay, you either fall here or you fall in here, for instance, or in here or in here, and how do you get there will be, I think, a combination of ands, but all of those together you are combining them with ors. And if we have that, we can turn it around, right? Like, imagine that we have, can we find another one? So this was for this. How about this one? PV goes up to here, and this goes up to here, and this goes up to here. It's a bit convoluted. Let's see this one. Okay, this one seems, I think, a bit shorter. So in order to fall into this accept here, we need that these two conditions to be false. So we need this not to be true, and not this other thing, right? So in that case, we know that if we fell into this, then we're going to be accepted. These two things are false. But we fall into this, if we get to here, and to get into here, we need this thing to be false, which actually in the previous one we needed to be true. So yeah, this is a combination of falsy things. And by the way, this was also a conversion of a falsy thing. And this, and then getting to px, which is, in order to get to px, this is the condition that needs to happen. So it is this condition again, so let's expand this here. So okay, these are two of the ways you can be accepted, with this accept condition, and with this, there's like 6 or 7 more. But with these two, it's like either this or this. So this has to be joined in with a giant or between these two, right? But we can convert an or into an and by applying De Morgan, right? And we can say, hey, this is this or this, or that is the same as saying not this and not this, negating all of that, right? I'm missing, yeah, like De Morgan is like when you have not A or B is the same as saying not A and not B. Yeah. That's the thing, like you distribute the negation and you change the and for or, and it works the other way, like not A and B is not A or not B, right? Not A and B, yes. But what if you have something that is not negated? So it would be, let's go back to the or. Not being negated, well, it's like a double negation, but then you would have something like this, which is like, not A and B, and like we can always convert, like every one of these is easy to convert to the negation. It's just switching the symbol and switching like less than to greater than or equal, and vice versa, and so on. Now having a not, can you distribute this here, like not A and not B? Like this can be converted to like positive things. So if you say, okay, not all of them together, well, it's sort of the same as saying then applying the or again. So yeah, you can, I guess, apply De Morgan again and go back to the initial thing. Does this solve things? Like, can we actually get to everything being ands or ors, or am I just tripping ands? Well, let's try it for this thing. We have this, okay? So let's apply like De Morgan. It should be ands, like it was like the negation of this and the negation of all of these. And there definitely are things that like let us simplify Boolean expressions. So this is not yet the same as this, because I think I still need to like actually add a level. This is like saying, okay, double negate everything and applying the, like not this, yeah, it's distributing the not inside and changing this to and, but this is the other, like we still need a not that surrounds everything, which to me feels a bit like not and. In order to distribute this here, we would have to change to do like the more again, but then you would have swapped those two things. So I don't know if we can simplify and change an intersection to like a union, because that's what, like, ands are intersections and ors are unions. So okay, let's think about it that way. Let's remove all the double negation thing and simplify this a little bit. So yeah, this is basically an intersection, right? Everything has to be true at the same time. So S, oh sorry, I got confused by, I thought that some of these were the same letters, but they are not. This thing is this condition, and the A was yeah, the not of this condition. Okay, so these are like three different intervals. So if S is less than this, if A is greater than this, and blah blah, right? This will give us like basically an interval for each of these things. So this is the same as saying A has to go from 2006 up to 4000. That is the new interval for A. And the same thing for S, the same thing for M. Now in this one, there is at least one of these that is duplicated, right? Let's find it. It's not S, it's not A. It is, no, it's S actually. S has to be less than 1300 something, and also has to be no less than this. So let's actually apply the negation here, which is easy to do. This is the same thing of saying it has to be greater than this. So if it has to be greater than this and less than this, then it has to go, like we can say it has to be in this interval basically. So yeah, I think we can sort of translate these conditions to intervals, yeah, and then combine these intervals. Right? It's kind of like that, although I'm not 100% sure, but yeah, we can, like S has to be less than this and greater than this. So we can, yeah, this is basically one interval. How do we combine? Like, how does the OR works? That's the question, because if all of this has to be true for this condition, oh, ORs are like these junctions, right? All of these ORs, I think, will be independent from each other, so we can just add up. Yeah. Okay. I think I kind of have it. I'm losing track of it, but like if you know, like S here, let's rewrite this into, let's actually rewrite all of this as like positive conditions, because I'm getting dizzy. So this is greater than, this is the same as this. M more than this, not M more than this means M less than or equal to this, sure. a less, not a less than this means less than, okay. So we have rewritten this. Let's put this together with the other s because they wanna hang out together. So s has to be less than this, which is saying which is the same as saying this has to be greater. No, actually I want it the other way around. This has to be less than this and greater than this, which is the same as saying this has to be less than or equal to s. And also, since all of these are integers, we can convert all of the less than or equal to just less than, because this is the same as saying, okay, if s has to be greater or equal than this, it means that it has to be just like greater than 536. So whenever we want to like negate something like less than or greater than, we can convert it into less than or greater than. We don't need to consider like the equals part. That's also a nice simplification. But okay, like then s here is this, like the condition for s here is like the intersections of those two like intervals, and x can be, well, it needs to be less than this. So these are also like intervals. Each of these intervals has a size, and multiplying all of this is like how many combinations of inputs of parts leads you to this acceptance outcome. And if all of these are disjointed, then the total will be adding all of this up, I think. And I think they are disjointed because like we did it like from the bottom up, from the leaves to the input workflow, but we can do it like from the top down and say, okay, what is the total condition for you to accept? Well, it is the condition, like if this matches, it's basically the conditions of this workflow to accept. So, okay, sorry. If this condition and the conditions of this workflow to accept, or, and there is our first or, the conditions of this workflow to accept. That is a single or. But then you would have like ors inside of all of this, so they be like nested ors, which kind of complicates the things. I think going bottom up simplifies things, at least in my head, a little bit. Okay. To me that sounded kind of reasonable. Now, how do we translate that into code? That is the question. Yeah, I think it's a big assumption to say that each of the acceptance branches is like disjointed from the others. Disjointed in the sense that what does disjointed mean in this sense? It's like no, yeah, but everything starts from the beginning. Like all parts will be either accepted or rejected, and the ones that are accepted by one of them means that those are things that, like the things that can be accepted here are things that cannot be accepted anywhere else. So I think it is fine to call these things disjointed. Treat them as disjointed. So is it fine to go from the bottom up, like finding all of the accepts and like doing that thing that I just did of like saying, okay, in order to be this, you have to match these conditions and not match anything that comes before, and match the condition that leads you there and not anything before that, and so on and so forth, like up to the in. Like that seems to me that it would work. But I'm wondering if I'm missing a simpler way of starting from the in and saying, okay, is this and whatever conditions goes in here, all of that, or the conditions there. It's like, give me your counts. Yeah, I think that's also like an or should be like addition of the cases, and an and is like a multiplication, right, of the intervals that make up those cases, I think. I think so. So you'd say, okay, this or this, and this would say this or this or this. Oh, but reject, what do we do about rejections? So we know, like, if we go like top down, we will find some things that delegate to other workflows, some things that accept, and some things that reject. So what do we do about the rejections? So, well, rejections are basically zero acceptances. So is the number of these things accepting or these things accepting, and that's it, plus zero. So yeah, I think that would still work. Yeah. Okay. And if a workflow has an acceptance here, what is that condition? Like, it's not just adding. I think ORs are not just adding. They are not just disjointed if we think of them like top down, because like think about this acceptance here. This one is easy because it accepts everything, but this one be like if s is less than this, it jumps to this. So if this and whatever makes this condition accept, or this condition and whatever, no, this rejects. So this is zero basically. If this condition is true, then it's zero, and if it's false, then we will accept. Oh man, it's kind of difficult. I find it a bit difficult to think going from the top of this like decision tree to the leaves. So I will try to do it now, going from the leaves up to the in workflow, and at least, I don't know, make these giant conditions, I guess. Yeah. Okay, but we have a nice solution. No, I don't want to close this. let's leave it as, I don't know, notes or whatever. We do have a nice solution for part 1. So first of all, I want to commit that. If we run check all, does this pass? I think we did. No, we didn't update the answers files. So is it compiling? Haven't I written this to the output file? Oh yeah, but part 2 is not working yet, of course. But day 19 we have this. Let's put it in the answers file. This is day. Oh, I didn't copy what I wanted. Copy and paste. Okay, and sure, we can commit this, right? It's going to fail on that one, but it passes the answers check. And I think that the code was generally very like top-down approach, but it's fine. We have all these debug derivations that I think are not necessary, but no, they are not necessary. Like if I need to print something now, considering like the conditions and stuff, I think I'm going to like write like an actual display implementation and print conditions like this, kind of nicer things. Yeah, we also have the thing about the lifetimes to kind of worry about and whatever. But I think the code in general like looks alright. Let's put this on the tab here so we have more space to look at things. So it took quite a bit of lines to write the part 1. First one for those parts, input, yeah, sure, that is fine. And everything else is just types, and like the main processing, so that's fine. That's fine. And each of these guys has like a parse part, which is, I think, overall more or less fine. And yeah, this is pretty nifty actually, how the rules do their things, like how the workflow delegates the processing to each rule, and yeah, this is kind of neat. I like this kind of thing. Yeah, this is pretty fine for part 1. Let's say add day 19 part 1 solution. Okay. Now for part 2. Okay, let's try to like write this thing, but I don't think I will care much about like delegation and stuff, because I will get crazy. This is kind of the difference between like sort of knowing what you're doing and not knowing what you're doing. Like previously for part 1, I felt like I really knew what I wanted and what I was doing, so I just, you know, called the thing that I wanted to exist and then implement. Like it was pretty easy to implement top down. In here, it's like I don't know what I'm doing. I don't know how this is going to work. So like I don't know what to delegate to, and this is like every delegation is sort of like a design decision that you're making, and if you don't know what you're doing, like you cannot design, you cannot make those sort of decisions. So let's actually say something stupid here, like answer 2 is going to say call part 2 with we actually don't care about the parts here, we just care about the workflows. So let's pass this thing and say part 2 generate and return a 64-bit number, which should be enough for this. And this is fine. Okay, what are we going to, and then just magically print the part 2 here. How are we going to do this? So I want to find all of the like accept rules and do this process of going up, and when we go up from our accept rule, we sort of are going to join conditions with and, basically, and after we do that, we're going to join all of those with, I'm not sure what we're going to do up to that point. Maybe I will just print what we get and call it a day and continue with this tomorrow and hopefully not go to sleep so late. But I want to try something. I mean, it has to be possible. Come on. Yeah, and about intervals, it's like if it has to be all of these and intervals or all of these. Like when you have these ands, these are intervals, and we have M, A, and S here. But this is also like there is an implicit interval here that is saying something like, what is the other X? X can be anything. X can be greater, let's say, like greater than 0 and less than or equal to, well, let's say less than 400 and I wrote this wrong, right? Yeah, something like this. There is this thing implicit here that doesn't say anything, but it's like, okay, this is the full interval for X. So if we want to say this or this, what would be like the corresponding intervals? But I don't know if that's actually possible to compute, right? Because it's not like M, we can say, hey, M can be this, well, maybe, yeah, this or this. Now I think here we do the Cartesian products, like multiply the size of all of these intervals, and then we add this to this, and we sort of try that out and see if that works, which is already quite convoluted on its own, so it won't be easy. But let's try to first find all the acceptance rules. How do we do that? Well, we want to find the rules whose acceptance are whose output is accept, so it shouldn't be this hard. Let's say yeah, but if we have that, like from a given rule, we don't know its workflow, so that's also part of like going from the bottom up. It's a bit difficult to know what you're doing. So can we generate this idea that we are thinking about, but going from the top down? I think the answer should probably be yes. If we start at in, it's like, okay, say S is less than this, like this would be one of the conditions, and get into Px. And then this is going to be okay. That condition and this condition get into this, and whenever we recursively like that we find an except like this, and like that will be a chain of ands. Yes, that will be a chain of ands. And then we kind of like push that somewhere. Yeah, that sounds reasonable. And then we say, okay, instead of this, make the opposite of this as the chain of ands that we got into here, and say, okay, and this, and that is also another chain of ands. Yeah, we can do this top down and make all of these like chains of conditions that we want. So let's try to do it. It's kind of and it's also kind of a recursive function, which is it's going to be a mess. So it's difficult to even think of where do we start. Yeah, we're gonna have like a thing that we are modifying, like a chain of things that we are so far modifying, and that we are, yeah. Okay, let's say something that we're going to have like a mutable and chain, whatever that is, a vector of, let's try to use some of these like model thingies, which might be useful. We're gonna have this, which we're gonna start as this. This is like the current chain, let's say. And let's also have like an accumulator for all the AND chains that we find. So let me add AND chains is in plural. It's going to be a vector of vectors of these things, whatever that's. Actually, let's say accept, yeah, like accept chains is what we want to put here. And then we want to have a function that we will like call recursively. I think it's going to be recursively. That will sort of work with these guys. A linked list, this also sounds like a job where a linked list will probably be better, but this is Rust. Vectors all the way. I'm pretty sure we don't need this kind of thing, and we can get it like by the way that we are doing recursion, but I don't know how to think about that, so I would think in terms of mutability. Yes, in terms of mutability, and maybe even like instead of using recursion, maybe I will use a while, a simple while loop with a reified stack variable. That also sounds maybe simpler. Like what is the current workflow that you are working, and then push and like pushing and popping. But in my head, this is kind of like getting into workflows kind of seems a bit recursive on itself. Although, well, I don't want to hit a recursion limit or something like that, but let's hope that doesn't happen. So difficult to think about these things. How are we going to like even start? Let's say, let's imagine that we have here a recursive, like I want to call something like collect accept chains, and we are going to pass the current chain, which is like empty at the beginning, sure, and we're going to also pass as mutable reference the accept chains, like the result of this. And you don't like this? Yeah, you do like that. Okay, we're sort of going to do this, and then we should magically have the accept chains, and then we need to like do this interval thingies, which is in itself not really not very simple, I think. The AND conditions, whenever you do a combination of ANDs, this is like this is for the intervals themselves. It's like they can only become smaller, and it's just intersection of intervals, so they don't get larger. That's nice. And I wonder, like, can't we, instead of having this, like, accept chains is such a complicated thing. Although we are thinking about conditions, right? Yeah. And not that, and not so on. I'm trying to think like this in terms of this thing that we had before, like the conditions, but maybe it would be better to think of like this as basically not current chain, but like a, let's say, an array of 4 intervals for the variables x, y, and or like x mass variables, and they would start like full, like from 1 to 4,000, and then whenever you are evaluating things, it's like you restrict these intervals with the different conditions. That sounds neat, actually, to do. And you end up then this like accept chains, so it would be like accept intervals, let's say. Yeah, because once you add more conditions, like the only thing that you do is you restrict these things a bit more. Yeah, that sort of sounds reasonable, I guess. Yeah, that sounds reasonable. And we did in a previous thing implement interval logic in day 5. I looked it up to like previously in this video, so we can copy things from there. Sure. Day 5. We actually even call it range, these things. And these were ranges like from a start point to an end point, but the end was not inclusive. Open-ended ranges. I don't know if for this case it might be more natural to express them as inclusive ranges. Although this representation has the very nice property that it can represent empty intervals, empty ranges very naturally, and probably we may want to do that if at some point, we need to cut an interval such that it becomes empty. It's like at that point no part could match that, and so I would bet that either doesn't happen on the input or if it happens, it's like you can stop like the recursion right there also. So yeah, that's also reasonable, I think. So let's actually say, okay, start intervals and just go for this, I think. Yeah, why not? We'll create an array of 4 interval things. And what is an interval? Well, who knows? It's gonna be a thing starting from 1 and ending at 4,000. Beautiful. Well, rationalizers is not yet as intelligent and saying, hey, yeah, I get you, buddy. I will make this thing. So this could be something like this. Then yeah, accept intervals. Yeah, this sounds reasonable. Where each of these variables start and end. Yeah. So let's have a struct struct interval, which will have a start. We are using 64 bits for everything, so let's continue with that, not thinking. And let's also have like a type for this array of 4 of these guys. So a type called, I don't know, var intervals. that is just going to be here an array of 4 interval. Whatever, I have no idea what I'm doing here. This thing, let's just, you know, from now on assume that this guy is for sure gonna be clone and copy, like for sure we want these things. So yeah, this shouldn't complain. And this is basically like a full interval. So we're going to start with this and say accept intervals is what we're going to do. And actually this may, instead of making it mutable here, that doesn't make much sense. Let's just pass copies of this, so we only care about mutability on this, and we are only going to put things in there when var intervals, when we find an accept condition. Okay, so we're gonna pass accept intervals and just the start intervals. Okay, sounds kind of reasonable. I don't know. This is of course a var intervals, and this is, now I don't want a slice, I want an actual reference to a vector because I'm going to push things into there. Thank you very much, and I want this to be mutable. So a vec of var intervals, yeah, and just not return anything. So this will need more things than this. It will also need the workflows for sure. So let's put that in there. And the workflows, of course. And should we pass like what is workflows? I don't know why I'm thinking that this is going to be like a recursive thing, but we are going to start with an in workflow. Yeah, and we are sort of going to recur into different workflows, I think. So it's actually pass like a sneaky in here, which is like the initial workflow. So let's also receive like a workflow ID, stir, of course. And here, what do we want to do? Well, we're gonna access the workflows for sure by this workflow ID. And in here, I just don't want to consider, like, worry about errors or things like that. So the IDs not being valid, like they should be valid. We're gonna have this. You cannot move. No, of course, don't move. Just grab a reference. So we are in the in workflow. What do we do? Well, we are gonna ask, hey, if the first condition is true, then collect the accept intervals to this. So like I want to restrict the interval that I got. This is not the start intervals. Let's say this is the cur intervals. And here's where I'm going to push. So how do we restrict something? Well, somehow, like, we'll restrict the current intervals by this, like saying s has to be less than this. So we will just change that interval to go from 1 up to this. That's what we are going to do. That sounds good. Yeah, that sounds good. And sure. We are using sort of inclusive intervals now, like how I wrote it. And they're equivalent to here. But otherwise, we're going to restrict the interval by the opposite of this and go into here. Yeah, that sounds reasonable to me. That sounds reasonable to me. So, how are we going to do this? Well, we have to go for each of the rules, basically. Evaluate for each of the rules. So how do we do that? Whenever we go to the next rule, we know that all the previous rules have been, we should like apply the opposite of all the rules to this interval to evaluate a single rule. Okay. Yeah, that sounds reasonable to me. So this is the current intervals. Yeah, let's say I think I'm going to get an interval and like start mutating it to like accumulate across the rules. Yeah, let's say let mute. So I don't know how to call it. I'm just going to call it intervals. And I'm going to, well, we can move this here if we're not going to reuse this, so that's fine. Then we're going to go for all the rules in workflow rules. This of course can be delegated to the workflow itself, but I'm incapable of thinking about that right now, so we're going to go for all the rules and we are going to consider the rule accepted, and otherwise we are going to mutate these intervals with the opposite of that condition. Okay, so let's say let's passing matching intervals and we're gonna have the rule here. I guess I will delegate just to like not think about this right now, but like rule I want to like or rule condition actually, rule condition, because we are iterating over all the rules. Condition I want you to like apply to an interval. Yeah, just or restrict interval. I get the intervals that apply to this rule, and I'm sort of like, if I could say, hey, give me the intervals that apply to this rule, and like, and it's like, and those conditions in a way, but I'm just going to say, okay, apply to intervals. I don't know, that's not a good name, but I'm going to apply to this. And let's just not mutate that and have a receiving thing. Like the matching, these are the intervals that should match that rule, that rule's condition. Okay, and so then I guess we need to know what the rule output is. So we're gonna match on the rule output, and we can do this. Okay, the acceptance, I think, is the interesting part. That is the interesting part. Yeah, if this are the matching intervals, so if the output is accept, we're gonna push this into the accept intervals. This matching intervals. Sure, go ahead with that. If it's reject and we match this thing, well, we do nothing, I think. We do nothing in that case because we don't care about that case. But we need to then go up to the next rule, because here we are evaluating all the things. All the things. I'm guessing that I will need to do some printing here, but let's leave that for later. And if it's a workflow, this is also a very interesting case in which we are going to recur and say, please collect the accept chains. I should rename this, is collect accepts intervals with this workflow ID and with the what intervals are we considering here? It's going to be the matching intervals for this rule, because this is, if we are matching this rule with this thing to push into, and with the workflows, which is immutable thing. Yes, okay, great. That makes sense in my head. These are the intervals of matching. Apply it intervals. Apply two intervals, let's say. Great. Let's sketch this thing. This should, take var intervals and return a var intervals. Sure, do it by value, I don't care. We're iterating here, let's not consume that, sure. Now, I said I was going to mutate this, and yes, I am going to, because I want to consider the non-matching. Now, these are the matching intervals. Let's now say, well, I'm just going to mutate this and say intervals is now going to be the rule condition negated, like the negated condition, and apply two intervals. Okay, that's, and yes, not to the matching one, because that will give me, I think, a empty interval, but to these intervals. All right, so in that way we have, I think, recurred through all of the rules. And then we need to consider the default or the fallback case for this. Which would have been, I think in this case, it would have been maybe easier to have a last rule that always matches, but well, hindsight is 2020. So still have to consider that. And I guess we need to just do a similar match to this. It's gonna be basically the same thing. If if the workflow fallback is accept, then we're going to accept intervals, push these intervals, that is the combination of not matching any of the rules. Okay, if it's reject, then well, nothing needs to be done no more. And if it is go to another workflow, we are going to recur in here also, and the intervals should be this, and the rest should be the same. Okay, so it's like cur intervals is like this. We can call this thing intervals, just, and we move it and mutate it. That's fine. Okay, so we also need to sketch out the negated thing. Let's generate this. The negated should give us back a new condition. Okay. So how do we do the negated of a condition? Well, we are going to return a new condition that applies to the same like index blah blah thing. So how was the, I think you could say like self, something like this. Yeah, oh, we are moving these things, which is like but this is like the last thing. We're going to need to change the right hand side value. So okay, let's write all of this. Like the blah 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 category index is going to be the same as myself. The greater than or less than is going to like the operator is going to be changed. So how are we going to do this? Let's say let's op and the, what was the other thing? The value, the match self, it will depend on the operator. Okay, and fill in those guys for me. And here we're just going to pass op and value. And you are unreachable, yeah, because of the to-dos. Okay, wait a second. Okay, if it's greater, if we're saying it's greater than, what is the same as negating that? Well, if it has to be like greater than 4, for example, that's the same as saying it can be less than 5, right? So operator, not the same. I mean, it's saying something is greater than 4, so it's 5, blah blah, or less than or equal to 4. So yeah, less than 5. So less than, and the value should be self value plus 1. Okay, and this I think is going to be the other way around. It's something that needs to be like less than 5, so it can be 1, 2, 3, 4. It's the same as saying it can be more than, greater than or equal to 5, so 5 onwards, or it's just the same as saying more than 4. So operator greater than and self value -1. Very nice and very symmetrical. That's the way nice code should look. Awesome. And then finally, we want to reduce these intervals. When we apply this rule to an interval, how are we going to say this? Oof. Well, we are applying a single rule to a single interval, so it shouldn't be this bad. We can get the interval that this applies to by doing something like let interval be the intervals indexed by self category index. That is the interval that this rule applies to, and then match the operator. And okay, if the rule says this thing has to be greater than something, that means the interval start has to change. Okay, so we're going to create a new interval. Yes. We can mutate it here, right? Yeah. Gonna change this guy, and we can say interval start has to be it has to be greater than something, so I guess greater than the value, but we sort of need to consider what. There's something that I'm missing here, and maybe having like the interval intersection that we were thinking before would be nice for this, because like the condition could have like an interval in itself and just say, hey, just do the intersection between that and my interval, and that's what you want to have. But okay, it has to be greater than a value, so the start has to be like that value plus 1, so self value plus 1. But imagine that this interval was already like, okay, the rule, imagine that the rule says, I don't know, x has to be greater than 5, but our interval itself was like, if it was 1 to 10, let's say, okay, then the result of this should be like 6 to 10, right? Because it has to be greater. Great. But if the interval was already like, I don't know, 7 to 10, and we say it must be greater than 5, it shouldn't change. It should still be 7 to 10. So we must get either this or like this, or the maximum with the interval start, like the maximum of those two. So interval start max, the max between these two. That's gonna be, and you don't like this because interval is an interval, and what's the problem? Oh, what we are returning? Yeah. Wait a second. This is not yet what. that's not yet what we want to do. Okay, and I guess the less than is gonna be like symmetrical, but in the other way. Now let's assume that the ends are inclusive, and I don't know, because we are doing sort of the intersection right here, I think. Yes, we are doing it right here, so we won't need that much logic. So let's also think in a similar way. We come to something like this, and it says, okay, it has to be less than 5, so it's gonna be 1 up to 4, sure. So this has to be self value, like this reduces the interval to self end to self value -1. But what if the initial interval was already little? Well, it has to be the same, so it's gonna be the interval ends mean with this guy. Okay, so I think we have sketched out. I don't think we are. Oh wait, this is to do, but this is just these intervals with this interval changed. So can we make a copy of this guy? Can we? I think we can, right? We can say something like we are receiving this, yeah, as a copy. So let's just say let mutes intervals. You know, we're just going to change them. Because like they were moved into here, so no problem with changing them. And here we can say intervals blah blah, take a mutable reference to this guy. So this is a reference to a guy that lives here in the stack, sure. We modify this guy, but then this is going to like have been modified in turn. And we return these ones, which is like the same thing that we got. I think I really like move semantics from Rust. It just clicks in my head. Okay, so where were we using this? Apply to intervals. So the usages are here. So okay, with this, if we have somehow made it through, we should now have a collection of accept intervals, which we can print actually. Print line. These are going to be a bit weird to read, so let's just print them one by one. Let's say for is intervals in accept intervals, print line, just the guy intervals. Yes, just do this. And you cannot be printed because of course intervals need to be debug. Where are your intervals? Here. Please be debug for a little bit. And can we cargo run this with this sample? Oh, it didn't, like, it hit it to do, but it didn't explode. I thought it had exploded. So wait, did we actually succeed in doing this shit? We do have some reasonable numbers, to be honest. And how many of this we have? 1, 2, 3, no. 1, it's difficult to count. Because, yeah, these are collections of 4 intervals each. I will make the font size smaller. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 of these, and in the sample we had oh man, I'm excited. This work. We had 9 A's here. Yeah, 9 out of 9. So we have the same amount of intervals as the acceptance conditions. That is promising. Although, okay, we did like simple recursion and we did hit everything, but that was nice. Let's see if you actually found like some of these, like m greater than 2090. So this is x mass. So for this, there must be one that goes from the x should go from 1 to 400, and there are actually quite a few of these. Okay, so it could be one of those. Then m has to be greater than 2090, so it has to start at 2091. So the second interval could be this, and this is the only one with this number. So is this the condition that we wrote there? My face is a little bit on the way. So okay, the first interval corresponds to x, so it's this. Second one corresponds to m, which is like greater than 2009. Then ma, so a has to be greater than or equal to 2006, yes, and then s has to be less than 1351, which is like up to 1350. And look at that, yes. So this seems like so far kind of correct. So okay, let's try to like do the actual calculation that we said that these things made sense to do. So actually, are there any empty intervals? An empty interval would be like an interval with a start that is less, or an end that is less than the start. There's nothing that I can see. But okay, like, okay, now, how do we do this? For intervals in accept intervals. So we are going to do something with this guys. Like what we are going to return is accept intervals. We're going to iterate these guys. We are going to map into like the Cartesian products of these guys, and then if they are all disjointed, that is the thesis of all of this, then we're just going to sum this up. Okay, and now what do we map into? This is an accept interval, so it is a variable interval, so we can call this thing intervals still, and this has like, it's a collection of 4 intervals, right? So we're going to get these 4 intervals. We sort of like do iterate again, map into something, and then make the product of this. The product is what we want now. And what are we going to map this each interval to? Well, basically the range, the size of the interval. So this would be end minus start. Let's say interval ends minus, and here it's like actually like give me your size interval. Like let's delegate this bit because hey, interval, this didn't have logic, but yeah, let's add some logic, why not? The impl for interval can be the last impl here. your size will be is 64, and yeah, this is an unsigned, so oh, actually I probably shouldn't have, well, it doesn't matter. So it's self end minus self start plus 1, because these are inclusive. And if the start is less than the end, this, like, the thing is empty, this will explode with an underflow, so we will know if that condition happens in the actual input. So we're gonna take the products, and yeah, is this what we want for answer of part 2? Oh, I'm a bit nervous. Let's run this. And we did get an answer. Is this the answer that we wanted? Where is the... Oh, no, I copied something wrong. It's just it. Yes, this is the answer for the sample. Oh man. How about the inputs? It didn't explode. It gave us a number. Is this the correct answer? Yes, it is. Yes. Oh man, I'm so happy. I didn't believe that I could get this thing at this time of day in this part of the country, localized entirely within my living room. But apparently my 2 neurons are still working enough to get a working solution for part 2. That's great. Let's actually copy this guy. Again, I'm constantly doing Control-C because Linux terminals have this thing of, they don't want you to copy things normally with Control-C. They want to use Control-Shift-C, of course. So, okay. Ah, man. This was something. That's great. And oof, the video is already like 2 hours, 10 minutes long. So, okay, what are we counting here? Oh, let's see the advent calendar. We just did day 19, and well, the avalanche of parts is still going on. Day 20 will still be on Desert Island, so I guess after we do day 20, we're going to have something falling into the island, which is going to be sand, if I remember correctly. Like, of course, the desert produces sand, and the island should produce water, and this in turn should produce snow. That's, yeah. What did I want to see from here? I have no idea. Yeah. So now we can check all. It should run. Yes, it does. Oh, what I wanted to see from the description is how many distinct combinations of ratings will be accepted. Ratings is the number for these numbers. So yeah, instead of like var intervals for this thing, is like ratings intervals. This is what I think it should be called. That's fine. And what we are doing here in what we called part 2 is combinations of ratings. Yes. Gets that will be accepted by the workflow. So gets accepts ratings combinations. That's not the best, but okay. Not the best name, but that's fine for me at this time of the day. accept combinations is gonna be this. And sure, this only takes the workflow. So the parameter, like the factoring of this, I'm actually quite happy of the shape of things in general. Like this thing just taking the workflows, you know, like things like make sense, at least I think so. So the starting intervals is all full intervals, yes. Full, let's say rating interval. Well, if I can write this correctly. Yeah, great. Then the accept intervals, yes, it's like an accumulator, sure. The order of things in here is very questionable because we are passing like the kind of output variable. Like at the third, let's pass it last, because this is kind of like an output variable, which we can, I think it would be difficult to return because like we would have to, well, we could like have a local variable here and push and then return. Yeah, that could work, but I don't think that's makes anything like particularly nicer. So I will just leave it as this. I think also like vectors in Rust, yeah, they have this nice property of like an empty vector, like not allocating. So that's also nice. You know, there's no problem of always returning a vector if most of those times is empty because you're not allocating things. So, that's actually something that we can try, you know? Like, okay, we have to change the order of this. Maybe that will make this thing a little bit better. Not so much, I think, but I mean, it's called collect, but accept intervals. Yeah. Well, let's see. Let's add this. And what if you say, okay, this is going to give me back the accept intervals. Let accept intervals be this. Boom. And this now is not going to take this as mutable, but instead return it like good citizens of the functional programming country. So it's kind of the same thing, but accept intervals, we can have it here. It's gonna be an empty vector at the beginning, and then what are we going to do? Well, we are going to sort of extend it with whatever we get from this. So sort of to accept intervals, extend is the, yeah, I think it is. Extend it with whatever we collect from here. That didn't complain, so. And here we are pushing a single one, which is fine. Which is fine. Mismatch. Did I Did I screw something? I did screw something at some point, but I don't know when I did it. Like, what's wrong here? Like, doesn't this need a comma here? I guess not. This is something about Rust syntax that I just learned, that these things doesn't need a comma after that. I was tripping by that. So we're going to do that. There we push a single one and then accept intervals. We are going to extend this to in here. Okay. And then we're just going to return these things. Does this make things better? I don't know. It just, yeah, I guess it's a little bit less mutability. Why not? And less sort of exterior mutability. It's like we are not passing mutable things to be changed around. It's like we do have something mutable here inside, but does it still work the same though? It looks like it. Great. That's fine. So inside, like what we're doing here is starting from this, count the accept intervals, and here we do this thing. Yeah, this I think doesn't need that much explanation. We do have, this thing is like intervals Cartesian products, sort of. So let's maybe put this into a little variable, which I would prefer to call it ratings, Cartesian products. And intervals is a rating intervals reference. Okay. Actually, I think that Rust allows to do this, though no. It's weird that from this usage it cannot infer the correct things, but that's fine. That's fine. We map this. This is fine. Sure. Interval size, yeah. This size function is a bit like, questionable, but yeah, sure, let's have it. Maybe we can delegate more things and make it a bit more like justify that the interval has a size. Great. So this code overall does more or less look good to me, although I'm not sure if my judgment is still like on point. But let's just review a little bit, over what we did for part 2. Then we are collecting accept intervals. This is interesting. We are receiving a workflow ID. This may fail. It's like, and here we're not handling this. So there is some, refactorings that I will probably try to do to this solution to maybe not work with workflow IDs as strings, and maybe just get rid of a lot of lifetime annotations on these guys. But I will probably do that off video or in another video. I also want to change a little bit of a shape in here. Process part was a thing for part 1, right? Yeah, so let's move the things that are about part 2 below this part 1 thingy, and actually let's move all of these things below this type annotations. And by the way, this debug is probably not needed anymore. yeah, let's put these things in here, and then goes the inputs of stuff. Just a little bit of code organization makes my head happier. Great, so about the collect intervals, is there something obvious that we can do here? We are going for each rule in this workflow, so yeah, for sure we could probably like delegate this thing to the workflow itself, although I'm not really sure if I want to do that. It does seem a little bit like, I don't know how I would even name this thing exactly. Like, well, yeah, I guess all of this is kind of part of the workflow itself, or could be part of the workflow itself, I guess, but nah, I don't care. Like, I would prefer this recursive thing to be like called by itself explicitly, like it's being done right now. This is fine. So for each workflow, we get like the intervals that match that. For each rule in the workflow, we get the intervals that match that rule, and then consider if that rule was an accept rule, then we know, yeah, that is an accept intervals. And otherwise, if it is going to a workflow, we recursively do this. So that's nice. Then when rule is not matched, or rule condition is not matched, we can continue with the rest of the rules. Or we continue with the rest of the rules, considering like this rule not meeting. Like, we continue with the rest of the rules, considering this rule, this rule's condition not matched. Okay, and this name, like, okay, condition can be negated, that is fine, that makes a lot of sense to me. And the code for this was, yeah, relatively quite straightforward. Can we like say change this and the category index stays the same? Kind of like this. Yeah, we can do that. These are the only things that change. That's fine. And then we do like this thing for the output is quite repeated, I guess. I'm thinking that maybe having like an always matching rule at the end of the workflow could have made this, you know, this would be part of this. So it would have been better, I guess, but I don't mind this repetition here. At least not right now. Okay, so that is all for part 2. I think it's pretty reasonable, all in all. I don't know if this was the best way to do this. There's probably some like more mathematical oriental way of thinking about this, but to me at least it made some sense, and it was some interesting reasoning to go through. So this should still all check. Awesome. And I think that will be it for this video. As usual, I want to do a little toilet thumbnail. So day 19, we are almost in the 20s. What did we do in here? well, a bunch of mathy things, a plenty of math things. I would describe this thing as like math recursion madness. Yeah, why not call it? Whoops, not in this screen. Here we're going to show some pretty and awesome code. Not really, not really pretty, but what we did, I would describe it as mathy recursive thingy. Yeah. That's the spirit. That's what we did today. A mathy recursive thingy for surely. And the code for this is, yeah, quite a thing. It's this basically. Look at that. It fits in a single screen, so it must be good if it's this short, right? So yeah, that's it for part 2. It was a very interesting part 2, I would say, and very interesting puzzle in general, because part 1 was all about like modeling things and like a very simple calculation, and was mostly about like parsing and modeling the things that you are working with. And then part 2 was like almost like completely the opposite. It was like hard thinking and like no modeling at all. Like it was mostly like just thinking about like the recursion patterns and what to do with the data, and like then doing some multiplications, and magically you get to the correct answer. So it was fun. And it was also 2 hours 30. So sorry for the long video, but if you have been, thanks a lot for watching, and see you later. Bye bye.